So, you want to add save functionality to your NES or Famicom homebrew software or game, maybe just to back up data or to copy that data from one console to another or distribute online. One option is to make use of the Family Basic Data Recorder or some other audio recorder to save your data, but you're going to need a way to connect that to your console. The Family Basic keyboard has audio jacks for this purpose, and my Pico to USB Family keyboard interface is getting it as well. But there are other ways you can add these connections to your console yourself. On the NES Dev Wiki page for the data recorder, there's a link to an example circuit you can use to add to the NES. And on Enri's page documenting the Family Basic, there is a representation of the circuit used in the Family Basic keyboard. But how are you going to encode the data to the recorder and then read it back? There are several ways this can be done. Many different standards have been used by various computers and devices over the years to encode data to tape. But I'm going to cover how it was done in the Family Basic here. Enri did a very detailed write-up of the Family Basic. I don't know where he got all the information, and it's really quite accurate, with the only major problem with it being all in Japanese. But that's not such a problem for me, but for aid of explanation, I'm going to translate it into English. The part we are concerned about is the CMT portion, which starts with the only major mistake. Out2 does not select the device between keyboard and CMT. The NES Dev Wiki is correct in that if you set bit to 0, you'll get a fixed value output. It mentions that the data encoding format is similar to Sharp's MZ or X1, and we're going to see that it is indeed the case. I'm going to use this write-up of the Sharp MZ700 example, the page recently gone offline, as a reference. Data is saved in two blocks, an information block or header and a data block. This is the same as the MZ700. You can see it here. The block starts with a gap. In the Family Basic, that gap is 20,000 short pulses. Though with the MZ700 there's a long gap that is 22,000 pulses and a short gap that is 11,000 pulses. At this point, it is probably worth comparing the pulses to show that they are essentially the same. First, let's have a look at the logical bit representation of the MZ700. You can see that a logical 1 is represented by a long pulse, and a logical 0 is represented by a short pulse. The pulse lengths are about 460 microseconds high, followed by 490 microseconds low for a long pulse, and 240 microseconds high and 260 microseconds low for a short pulse, with the read point taking place at about 368 microseconds after the rising edge of the signal, transition from low to high. This means that the long gap takes about 9 seconds to write and read from the tape, and the short gap about 4.5 seconds. So, what about the Family Basic? We're going to have to take a look at the code. Most of the work on this disassembly of Family Basic was not done by me, but I have done work particularly on the save and load functionality. The routines for writing bits to the data recorder look like this. Two counters are set up as either hex 34 or hex 60A, 6A. For a short pulse or a long pulse respectively, which means the long pulse is roughly twice the length of the short pulse. Then the first loop will output a low signal, followed by a high signal for the length of the counters. Seeing out 0 does not go through an inverter on the way to the expansion port, this means the signal is inverted representation of the MZ700 page. But that page also notes that the physical values may be contrary or change depending on the device. And when we look at the reading subroutine, we find that the timing delay is hex 4E for sampling the input. But how long are these pulses in microseconds? My scope shows that the short pulse is at around 220 microseconds high and low. The long pulse will be about double that, with the reading times being halfway in between. So all in all, close in timing to the format used by the MZ700. This would make the two 20,000 short pulse gaps in the Family Basic, each around 8.5 seconds, meaning around 17 seconds of each save and load operation is just reading or writing those gaps to the tape. My assumption for the use of these gaps is really so that users can more easily locate their saved data on the tape, with some time to actually start the load operation after the tape beat begins. If you're planning to use a digital recorder to manage your saved data, these gaps could be significantly reduced. But it is worth having some gap in the format to ensure the program locks onto the data stream before it needs to be reading the data. After the gaps come tape marks. A long tape mark for the header block and a short tape mark for the data block. This is the same for both the MZ700 and for the Family Basic. They both use 40 long pulses followed by 40 short pulses for the tape mark, and 20 long pulses and 20 short pulses for the data block, both followed by a single 1 long pulse at the end. These tape marks are counted on by Family Basic while the gaps are not. If the expected tape mark is too long or too short or has a bit flipped, the load will fail. Next is where the Family Basic really separates from the MZ700. After the tape marks, there is header data, and the data blocks come in both formats. But on the MZ700, there are 2 copies of the header data. Header data 1 and header data C, and file C. While on the Family Basic there is only a single copy. Both use a 2-byte checksum for each of the blocks, and in both cases the checksum is made by counting the number of 1 bits in the blocks. So that is another point of similarity. The final point of similarity is how the bytes are stored. On the MZ700 and in Family Basic, a byte starts with a 1 bit, followed by the most significant bit to the least significant bit, making a total of 9 bits per byte. Now that's over with, let's take a closer look at the contents of the blocks of data. The Family Basic header is 128 bytes long, but only really uses 24 bytes. The first byte is the type of data being stored, basic program code or background graphics or sprites. If the value is something other than hex 2 or 3, the data will not be loaded. And we can see this in the memory viewer as well. This is followed by a 16-byte space for a file name. By default, this is filled with hex 20, the character for a space. The file name will be null terminated, and this block ends with a 0 byte to terminate the default file name. The next 2 bytes are the length of the program data, meaning that a maximum of 32 kilobytes is possible, but only a maximum of 4 kilobytes of 0 available. The following 2 bytes are the load address, the position in memory where the data will be copied to, and then 2 bytes show the execute address. If we look in the Family Basic memory, we can see there are 4 more bytes past the execute address that are hex 20, but don't seem to be used. And the rest of the 128 kilobyte header data is just random. Likely this is just whatever the memory contents were when the console was powered on, and adds to the checksum to ensure data integrity. The data block is simpler. It is just a straight copy of the Family Basic program data in memory starting at the load address, which should be 6006 hex. Yeah. Each basic line starts with 1 byte for the length of the line, a line number, and then the line contents, which is also null terminated. When the line length is 0, that indicates the end of the program. Family Basic also stores the location of the end of the program in memory. So the length of the program can be easily calculated by subtracting the start from the end. With the format out of the way, let's get into the nitty-gritty of the actual routines to save and load data with the data recorder. These could be the basis of how you might implement saving data in your own program. Let's start with saving data. The first part is building the header data in memory. Family Basic uses the address block at hex 0500 to 058 for this. Then the routine is called to write out that data. The first thing that happens is that NMI interrupt is disabled. This is important. An NMI interrupt at the wrong time could turn a short pause into a very long pause, corrupting the data. And at 60 FPS you'd have more than 500 interrupts in the gaps alone. Next, pointers are set up in memory. For the start and end of the header block will be written out. Let's have a quick look at that. Here we are. These pointers are set up in the 0 page. Then hex 28, decimal 40 is loaded into a counter, and then we jump into the right routine proper. A 20,000 counter is set up, and then it loops through that counter right in short pulse down here. We already had a sneak peek at the pulse writing code before, so I won't cover that again. Once the gap is finished, the 40 counter is loaded, and we write out 40 long pulses, and then we write out 40 short pulses. Once that's done, we write out one more long pulse, and then we set up the checksum bytes. 2 bytes are set up for the checksum, and then using the pointer, we loop through the pointer addresses that are set up earlier, writing the bytes to the data recorder. The start address is incremented and then checked to the end address for exiting the loop. The low byte of the checksum is pushed to the stack, and then the high byte of the checksum is written out to the data recorder first, with the low byte pulled from the stack and then written out afterward. Last is a single long pulse. The low byte of the checksum is put in the stack before the checksum is written, because writing the bytes to the recorder increments the checksum, and you don't want the checksum to change while it is being written. The routine that handles writing the byte to the data recorder goes like this. First a long pulse is sent. This doesn't count towards the checksum. Then a counter is set up. The byte that is written will be currently in the accumulator, which is saved to 0 page address 14. The carry is cleared, and then it is added to itself. This essentially multiplies by 2, which will push the most significant bit off onto the carry bit. Why this is done and not an arithmetic shift left, I don't know. This way takes 3 cycles longer, which could be intentional or it might not be. Regardless, if the carry is set, then we will branch down to this routine that will write a long pulse. It will increment the high bit counter for the checksum, and then it will jump to decrement the loop. If it was not set, then we'll write a short pulse and it will fall into the loop decrement. Once the loop is done, we just return. Once the header is finished being written, we'll re-enable the NMI and it returns to the save handler. Saving the program data is mostly the same, but with a different entry point down here. The NMI is disabled again, and then we set up different pointers. We'll see that here. This time the end address is derived from the start address and the length. Add them together to calculate the end address. One could easily change this to store the end address in the header rather than the length, negating the need for calculation here. Then a 20 counter is set up for the data tape mark, and the rest is the same. One thing to note is that during the save operation, input is not checked. Once it is started, it will run to the end regardless of input, apart from powering off the console or resetting it. It does not care if your tape is recording, it does not care if you hit the end of the tape. Once you have started, you have to wait for it to finish. This is not the case with the load operation. Once the load operation is started, you're stuck in it until an error or a valid file is loaded. So it will check for the stop key to be pressed and abort the operation. Let's take a look at the load operation. Again, NMI is disabled. This time it would lead to missing bits from the data recorder. We store a 0 in the 0 page B1 to signify we're loading data, not validating. More on that later. And then pointers are set up for loading data into the header at memory address 0500. We'll have a look at that as well. A 40 length counter is set up, and we enter a loop reading bits from the data recorder for the header tape mark. While tape marks are long pulses followed by short pulses, ones followed by zeros, because reading from the tape comes back to the console through the controller inverters, the result is inverted. So the first loop is looking for 40 zeros and the second for 40 ones. I'm not entirely sure why they didn't just skip the final inverter in the circuit inside the Family Basic keyboard to return it normally, but here we are. If any bit in the two blocks is not as expected, the routine will reset to the beginning of looking for a tape mark. Seeing we're here, let's see how reading bits from the tape recorder is handled. The first thing is to wait for the right time to sample the output. This wait routine will jump to a routine that will poll the keyboard to check if the stop key is being pressed. If it is, it will return with the carry set to signal the outer routines to abort. If stop isn't being pressed, it will read from joypad 1 and logical and the output with hex 2 to check the output from the data recorder. The first loop will remain while the result is 0, which means the signal is high on the tape. Then the second loop will remain while the result is hex 2, meaning the signal is low on the tape, and then it will return. If we look at this visually, the signal will be either high or low after reading. The routine needs to wait for the signal to go high in order to read the next bit. So if the signal is already low, it will pass through the first loop and then wait in the second. While if the signal is high, it will wait while high and then wait in the second for the signal to go high. Carry is cleared before return to assure the program that there is no error. The counter is loaded with hex 4e, which is the timing for sampling the output from the data recorder. The counter counts down, and then joypad 1 is read, and logically AND with hex 02, and then returned with the carry clear. So we've made it through the tape mark onto the data itself. This is mostly a reverse of writing the data. We set up a checksum again, and then wait 2 bits. The final one and the leading one of the first byte of data. Then we read a byte from the tape, then check B1 to either load data into memory or compare it with memory for validation. Don't worry, I'll get to that later. We increment the memory pointer down here and do a check to see if we're at the end to continue looping. Let's have a look at reading a byte. We start off here by setting up a loop counter, putting a 0 in 0 page 19. This is where we'll store the byte we load. Again, we multiply the value in 0 page 19, pushing it off the top bit and then reading a bit from the data recorder. Again, checking for the stop key. If it is not pressed and the result is not a 0, then we read 0 and we decrement the loop counter and we loop. If it was a 0, then we read it as a 1, we increment the checksum counter and we increment the value in ZP19. Finally, when the loop is done, we wait for one more bit. This is the leading bit of the next byte for some reason. We load the value from ZP19 and then we return it. Once the entire data block has been read, make a copy of the checksum and then read and compare the checksum bytes with those copies so we can return to the load handler signaling either success or an error, re-enabling the NMI of course. The program data is much the same as you can guess, with one major change there being a separate entry point to set 0 page B1 to 1. This is taken if you type load ? Or load print and will compare the program in memory with the program on the data recorder, giving an error if they don't match. The pointers for loading the program data are calculated the same way as when writing the data to the data recorder, and the rest is essentially the same. So now you know how Family Basic saves data to the data recorder, and how you can do it too. Let's look at it a little bit more in action. Let's start by loading some data I prepared earlier. I have the memory viewer on screen so we can see how the program works in memory. You can see it's loading and it's picked up the name Hello World for the program. So the first program is loaded, we can list it, we can run it. Now let's look at how validating the program in memory works. We do load with the question mark. And we run it again. This will take some time. You can see it has picked up the file name. And there was no error, so we know that it has validated correctly. Let's load a different program to see what happens when we get an error. You can see now there is no file name listed as it's loading. And we get this error, TP error. Next, how about loading with a file name? We can see in memory that this program had a file name and it loaded fine when I ran load without specifying a file name. But what happens if I specify the file name and load a different program? So with no file name specified, any program will be loaded. But if you specify a file name, any program with the incorrect file name will be skipped. So let's use the right file name this time, the correct file. Now it jumps into loading Hello World. And we get the file loaded. Finally, let's make a new program and let's save it out. So I'll just do something simple. So that's my simple program. I seem to miss keys sometimes. I think that might be a Family Basic problem, the way it's pinning the keys, but that's alright. So first we have to start our tape recorder. If we don't start our tape recorder first, we won't get it. Anything. And now we save. And we can see that mostly 20s for the file name. The length is 2D. And we are starting at 6006. We have a look at the save RAM. You can see that it's cut out that much there. And we're finished writing. And now we stop our tape recorder. As one more demonstration, I've implemented save and load in my MS Basic fork for the Famicom, based on how Family Basic uses the data recorder. Support for file names and load abort still needs to be done, but I can at least save and load programs. Let's load the Blackjack program I ported. You can see the header data turns up in memory much sooner than with Family Basic. The gap lengths I chose come to about 2 seconds. You can see the program data is loading properly as well. Loading was a success. Let's run the program first. Actually, let's list it. Here's the program listed out. Let's run it. You can see that Blackjack is running properly. Let's hit busted one more time. Let's hit it. Busted. I'm not very good at this game. Lastly, I'm going to leave you with the soothing sounds of the Blackjack program recording. I hope to see you here again.